look at, this is when the base is greater than 1. And the second one will be 0 less than a less than 1. What does that notation mean? So it's between 0 and 1, so it's a fraction. Okay, so this might be 2 to the x, 3 to the x, 5 to the x, 10 to the x. This will be 1/2 to the x, 1/4 to the x. Exactly. So this one you already saw goes like this. That'll come, but these are just the base graphs. When you have a fraction as the base, the graph flips. Goes the other way. So an example of that could be the more girls you add, the less studying that's getting done. Okay, more girls, way less studying. So characteristics of exponential graphs. The graph has a horizontal asymptote at y equal to 0, so let's draw that in. So it never crosses the x-axis. Why? Why does it never cross the x-axis? Say that a little bit louder, David. Could there be negative stupidity? Perhaps. So if I gave you, let's say 2 to the x, is it possible to put in a value for x and get out a negative number? So 2 to the x, if we put in any positive number, so 2 to the 3, for example, what are we going to get? 8. And 2 to the 4, 16. So any positive number I put in, the number is going to get bigger and bigger. What if I put in 0? We talked about that. 2 to the 0 is 1. Well, what if I start putting negatives? So 2 to the negative 1. That's our Friday equals 2 to the negative 1 equals a half. 2 to the negative 2 equals a quarter. 2 to the negative 3 equals an eighth. Am I ever going to get out anything negative when you're dealing with exponents? No. So that's why there's nothing down here. It's impossible. There's no way to put an exponent in and get a negative answer. So that's why the horizontal asymptote is always at y equal to 0. Because there's an asymptote at y equal to 0, the graph does not have an x-intercept. The graph has a y-intercept at 0, 1. The domain for either of those? And the range for either of those? Ooh, greater than, not equal to. Okay, so let's graph base graph of 3 to the x. Okay, and just like when we started transformations and you didn't know what base graph looked like, we started with table of values. And we've talked before, you can pick any x values you want. We usually want some negatives, usually 0, usually some positives, so give me some numbers. Anybody give me a number? 1, 2. Well, we want some positives, 0, probably some negatives. Okay, so putting x as 1, 3 to the 1. Putting in 2, 3 to the 2. Three to the 0. 3 to the negative 1. So we'll just do that one off to the side. Okay, exponent law says if you have a negative exponent, what happens over here? It goes under 1, and so we get 1/3. And so following that pattern, if we had 3 to the negative 2, would be 1 over 3 squared, which is 1 over 9. Okay, so just graphing the points, 1, 3, 2, 9, 0, 1, negative 1, a third, negative 2, a ninth. Horizontal asymptote. Okay, so just showing why the shape is what it is. Later on in the unit, we'll do applications, and you'll see this comes up in almost every single science. You have exponential growth in biology and physics and chemistry and economics. So let's go back to transformations, because these can have transformations just like any other graph. So what was the trick before to know whether a transformation was horizontal or vertical? That stretches compression, so you're kind of on there, but horizontal versus inside brackets and outside the brackets. It changes slightly with exponentials. If it's up in the exponent, it is horizontal. If it's down in the main equation, it is vertical. So vertical in the main equation, vertical in the main equation, horizontal in the exponent. Okay, so let's describe all of these. A is just the base. It's not a transformation. It's just the base graph, whether it's a 2 or a 3 or a 1/2. B, first thing you want to ask yourself, is it in the exponent or down in the main equation? So that tells you it's a horizontal something. Then just like before, if you're multiplying, it's a stretch or compression. If you're adding, it's a translation. If it's a negative, it's a reflection. So is this a multiplication or an addition subtraction? So this is a horizontal compression. Why is it a compression and not a stretch? Because it's a whole number. So same rules as before. Whole number in the exponent means it's a horizontal compression. C, is it in the exponent or down in the main equation? So that means it's vertical. Is it a multiplication or an addition subtraction? So that means it's a stretch or compression. Is it a whole number or a fraction? Whole number, so that means it's a stretch. We're assuming it's a whole number. D, in the exponent or down in the main equation? So right away that tells you it's horizontal. Is it multiplication or addition subtraction? So that tells you it is a horizontal translation. H, in the exponent or down in the main equation? So that means it's vertical. Is it a multiplication or an addition subtraction? Translation. Okay, so we're just bringing unit 3 into these new kinds of functions that we're looking at. So just like unit 3, we're just going to name the transformations. We don't need to draw this. We just want to make sure we know what they are. First thing we need to do with this left-hand side. So just like unit 3. The 4 is not a transformation. What is it? It's the base. So in this case, what is the base graph? We'll strip away all the other numbers. You need a base and you need an exponent. So the base is 4. The exponent is x. Okay, so base graph is 4 to the x. So I just took out all the other numbers besides that base. Okay, I have the negative, I have the 2 that's in front, I have the 2 within the brackets, and I have the 3. the negative in the exponent or down in the main equation? That tells you it's vertical. It's a negative, so it has to be a vertical. The 2 down in the exponent or down in the main equation. So that means it's vertical. And it is a vertical stretch. How do you know it's a stretch and not compression? Whole number. The other 2 in the exponent or down in the main equation. So that means it is horizontal. Is it a multiplication or an addition subtraction? Whole number or fraction? Whole number, horizontal, compression. And the 3 at the end, down in the main equation or in the exponent. Main equation tells you it's vertical. Questions so far? Okay, now we're going to draw them, so just like we did in Unit 2. We're going to sketch the graph of y plus 4 equals 2 to the 2x, and Kelsey, domain and range, don't let me forget. Okay, strip away the numbers, base graph. So you're looking for the base and the exponent of x. What is the base graph? Until you get to know what these graphs look like, we're just going to do a little table of values in our head. If you want to write it down, you can write it down. So I usually start with 0 because it's the easiest. What's 2 to the 0? So we know that it's got a y-intercept at 1. Now I'm going to go to 1. So if x equals 1, we have 2 to the 1, which is 2. If I put in 2 for x, 2 to the 2, not a trick question, 2 to the 2, 4. Now to get the negative side, I'm just taking these values and making them fractions. So 2 is going to become 1 over 2, which is a half. 4 is going to become a quarter. If I want to keep going, I would have had 8. It would have been an 1/8, then a 16th, then a 32nd. So we know it approaches the x-axis on the left and sweeps up on the right. Okay, once you draw enough of these, you'll know what the base graph of 2 to the x and 3 to the x looks like. For now, just a little table of values till you figure out the shape. Okay, let's identify the transformations. What should we do with the 4? Okay, left to right, first transformation is the little 2 in the exponent. Second is going to be the minus 4. So the 2 in the exponent, we know that's horizontal because it's in the exponent. It's a whole number, so it is a compression, and it says xy goes to x over 2 y. So we haven't changed anything from Unit 3. Mapping is still the same. Second transformation in the exponent or in the main equation. So that's vertical. It's addition, so that is a 4 down. It depends on the question, so I would do it no matter what, because then you're not going to lose marks. So get in the habit of just like Unit 3, right? We did it there. So if you're a point person, we'll just go from the original points, which was -2, a quarter, -1, half, 1, 0, 1, and 2. Okay, we want to divide all the x's by 2. -1, a quarter. -1/2, a half. Okay, if the points wasn't your thing in unit 3, we can just do it now from the graph. So 2 is going to go over to be 1. 1 is going to go over to be a half. The y-intercept doesn't move. 1 comes in to be a half. And 2 comes in to be 1. After each step, what do we pause and ask ourselves? Did we do what we said we were going to do? So horizontal compression, did we squish this thing in from the left and the right? Did it get squishier? Okay, vertical translation. This is the first time we're kind of seeing this with asymptotes. Asymptotes follow with the graph. So if the graph is moving down, the asymptote's going to move down. If you have vertical asymptotes and the graph's moving over, the asymptote's going to move over. So let's do that first. If it's at or y equal to 0 right now and it drops down 4, where is it going to be? Y equal to negative 4. So asymptotes move with the graph. We're okay if they're both in red because we understand what's going on. Red pen now because this is going to be our last graph. So what we're doing is dropping it all 4. Oh, I want to say that last one should be on the x-axis. Don't get too caught up with these points on the left-hand side because we know it's just approaching the x-axis, so we're not going to look in there and, oh, you have it at a third and it should be at a quarter. We're just generally looking for the shape of the graph. Is it approaching the x-axis on the left? Is it going up towards infinity on the right? Are your intercepts correct? Good to go. So we're not going to get really fussy in this area as long as it's approaching the asymptote. Typically, we do the 2 intercepts would be the minimum amount of points. Do you see the link to transformations? Okay. All we're doing is changing the base graph. So now you've got base graphs that look like x squared, x cubed, square root of x, absolute value of x. Now we can add in any exponential. Domain. Offer of XER. The range. Okay, so the range changes because of the vertical translation. Okay, so let's do one with a fractional base. So take away all the numbers except for the base and the exponent. So exponent's always going to be x. You start to figure out what is x attached to. So what is the base versus transformations? What's the base? A half. And again, until you get really comfortable drawing those, just table of value it. No big deal. We already know what does the general shape have to look like if the base is a fraction. The opposite. So we know it's going to end up going like this. So let's prove why. Give me some numbers. That kills my left brain that those are not in order. It drives me nuts. Okay, so 1/2 to the negative 1. So you need to know your exponent laws pretty well for this. I'm just going to grab paper. 1/2 to the negative 1. So irrelevant of the base, what's the rule with negative exponents? Kind of. So it goes under 1 and the exponent becomes? Goes under 1 and the exponent becomes? Positive. So I'm just going to write the +1 so you see where the negative went. Okay, what's anything to the exponent of 1? Itself. And how do we divide fractions? Multiply by the reciprocal, which would be 2 over 1. So 1 times 2 And on the bottom, imaginary 1 times 1. No, I'm just showing you where it's coming from. All of this turns out to be 2. So a half to the negative 1 equals 2. Okay, a half to the negative 2. Okay, exponent law says it goes under 1 and becomes positive. What do we do when we have a fraction with an exponent? We square both of them or apply it to both. So 1 squared and 2 squared. So 1 half to the minus 2 equals 4. Then when we get to 0, we're like, yes, anything to the 0? No thinking. Anything to the 1 itself, so that has to be a half. A half, or a half squared, quarter, so square the top, square the bottom. Okay, so negative 1 and 2, negative 2 and 4, 0, 1, 1 1/2, 2 1/4. Asymptote. So here's why the fractional base makes the graph flip. Okay, transformations, the negative in front. Vertical reflection, xy goes to offer of x minus y. Okay. The minus 4 that's in the brackets. Four to the right. So it's got that backwards feel just like in Unit 3, that if it's negative, it's going to the right, positive, it's going to the left. Okay, if you're a point person, you can work off the table of values. If you're not a point person, you can go straight to the graph. Vertical reflection means we're flipping what way? Down, so up's going to down. So this one right now is at negative 2, 4. It's going to go to negative 2, negative 4. Negative 1, 2 is going to go to negative 2. 0, 1 is going to go to 1 1/2. And we're going to pause and say, did I do what I said we were going to do? Did we flip this thing vertically? So top went to bottom, bottom went to top. Okay, so exponential graphs can be on the bottom if we have a transformation that put them there. The base graph cannot, but sometimes transformations will end up making them in the negative, and that's fine. Last step, red. So do we need to move the asymptote? Nope, because we're doing a horizontal shift, so it's not going to move up or down. We're moving everything 4 units to the right. And again, don't get too caught up with these halves and a quarters. As long as it's approaching the asymptote here, we're not going to look at your individual little points. We just want to know, does the general shape look like it should? Put your finger in the air. So now I can add, draw me an exponential graph. Okay, so comes along, swoops up is exponential. Okay, word problem. Oh, thank you, domain range. Domain? Range? Or equal to or just less than? Less than 0. Okay, read to read. Don't stress out. Just read it like this is a really boring book. It's just a little sentence in a book. So we're going to pretend with this one that we aren't mathematicians. We are the scientists that are now looking at data. So mathematicians would give this equation. Mathematicians are the one that would mathematically come up with this. They now turn it off to the people who actually use it. So as scientists now, we have to use this equation to figure out a bunch of stuff. Keywords in the main part of the question. Still a little bit more I would do. We know the units for n, but what does n represent? And what's a host? Number of computers. How do we know by looking at the equation that it's exponential? So how do you recognize an exponential equation? Well, let's back up. How do you recognize a parabola? How do you recognize a linear function? How do you represent a cubic? How do you represent recognize a radical? It has a square root in it. How do you recognize a rational? Does it have to be 1 over the function? No, it's just a polynomial divided by a polynomial, so it's a fraction. How do you recognize an exponential function? Variable in the exponent. So if you didn't readily know the answer, jot that down. So you recognize an exponential function because the variable is in the exponent. Okay, so question 1 is just saying graph, so go into your y equals, clear out any crap you might have in there. Okay, typing in exactly what it says, so 7.4, 1.59. How do I do an exponent? Okay, what do we call it in math? Call it a hat. What does everyone else call it in every other science? Caret. It's called a caret. And then we're just going to use x because we don't have a t at this point, just x, just a variable. Okay, what is this stuff in part A about 0, less than t, less than whatever? What's? Yeah, that's telling you the window. It's telling you where to set which of your variables, x or y. How do you know that this is asking you to solve or to set x from 0 to 20? Because x is in the equation where t is. Okay, so window, they're telling you that your min should be 0. They're telling you your max should be 20. They haven't told you anything for y, so we've got to kind of figure that one out on our own. What's the lowest that y could be? Okay, has to be 0. What's the highest y could be? Well, what does y represent? Number of years after 90, yep, was 95. Why after 95? Why is that an important year? Because that's when the internet went live, right? The internet actually has been around since the 70s, but was only used for military because it was like a secret defense. And then about 95, they're like, okay, everyone can have access to it. Okay, so how many years do you think is appropriate for the height of our graph? So we want to look 2,000 years after 1999? So if I put 2000, what am I saying here? 2,000 years after 1999, so probably that's a little too much. So 20 years would give us what year? Now, 2015, so that seems good. Okay, hit graph. How do I show work for part A? Draw the graph. Now, because this is a word problem, I can actually label the axes. So I don't want to just leave it blank like this, like we usually do, which is x and y. We can actually give variables and units and what it is. What's the bottom axes? Time. And the units is years. And the y-axis. And the units is okay, part B. What should we highlight? Okay, so they're asking for an x or a y. They're asking for the y, and they've given us x, okay? How do we use a calculator to find any y value given an x value? Okay, so second calc gives you anything you want to calculate on a graph. Value, but don't we use that for x-intercept or y-intercept? Why are we suddenly using it for something else, which I hit the wrong one? Yes, I did it again. Correct. So we usually put in 0 to get the y-intercept, but we can put in anything. Now, use your brains a bit. We're not putting in 2010. Why is it 15? So how many years between 1995 and 2010? 15. Hit enter. Okay, so answer for B is? Would a mathematician ever say this? What would a mathematician say? We would never say 7,000 million.
7.766 times 10 to the 7 or something.
We have a word for that. Billion. If you gave this, that would be a half mark off. That's like saying 1,000. Okay? Never would I say my salary is a 1,000. Because you should know once you get over to 3, then million disappears. The most you can have is 999 million. What's the next value after that? A billion. Why did I put a what? Yeah, because now this is billions. So now it's 7.7 billion rather than 700 whatever thousand million. Okay, what about C? I'm actually looking for some highlighting. Okay, so are we looking for an x or a y? We're looking for an x value. Okay, how can we use the calculator to find an x value if they've given us a y? Okay, go into y equals.
Go to y2 and say 1,000.
Oh, what are we doing here? So where have we done this before? When we're jumping down to y2. We are solving an equation graphically. So all they have done is they have given you n. So they've told you 1 billion, which in terms of millions is 1,000, equals 7.4 times 1.59t. Okay, so this just now becomes solving an equation graphically, which we've done in 3 units. So jump down to y2, put 1,000. Probably we want to change our window. Which one are we going to need to change? Okay, was that a good choice? Can we see the intersection of the lines? How am I going to show work for this? Because this is just solving, we don't need units or axes. We need the graph and okay, second function trace. Do I need to? Yeah, if there's only 2 graphs, you can just hit enter because the calc knows. Okay, now we just need to understand what the question's asking and what the value means. So 10.57, what does that mean in terms of our situation?
It means 10 because it's discrete. Because like you can't half a year you're good enough round.
So it's going to be between those 2 years. So what do we call it when it's between? Well, we need the actual year. So 10 years after 1995, 2005. We would never say 2005.7 or whatever it was. We say it happens in 2005. If it's July, if it's May, if it's March, it's 2005. Okay, so if I said, what year did you turn 16? Do you round that up to the next year? No, because it's still within that year. So no rounding with years. Questions? There's only like 6 minutes.